we are going to discuss how to perform integration where the integrand is made up of a fractional function with a denominator such that it contains a repeated irreducible quadratic factor. This is an example of the integrations of a fractional function where the denominator function is made up of the product of three terms. The first term is a linear factor, whereas the second and third terms is made up of a repeated irreducible quadratic factor, x squared plus 1. According to the rules of partial fractions, the rational function r has to be decomposed into the partial fraction of three terms. The first term in the partial fractions comes from the linear factor, and for the linear factor you always assign a constant to it. The second term and the third term are coming from the repeated quadratic factor x squared plus 1. The third term is the repeated quadratic factor x squared plus 1 raised to the square. For each of the irreducible quadratic factor, you have to assign a linear factor to the corresponding numerator. Here I'm going to assign this as bx plus c, whereas for the third partial fraction, the numerator dx plus e. Here let us try to integrate the term a, b, c, d, e on the right hand side of the partial fractions. The integration of the first term involving x is simply a log of x. The integrations for bx plus c has to be performed independently. So let me perform the b term integrations, which is x over x squared plus 1 dx. The integration of this term can be done by using substitutions. X squared plus 1 to be substituted by y. dy is x dx. So the integrations of x dx is now reduced to dy over half, and the denominator is y. So here you got b over 2 and y. So that finished up the integrations for the b term. Next, we go to the integration for the c term, which is this one. So it is integrations of c dx over x squared plus 1. The integrations can be easily obtained by referring to the integration table, which we have seen earlier on. The integrations of 1 over x squared plus 1 can be referred to the equation of 19, where a is said to be 1. So the integration of 1 over x squared plus 1 is simply arctan of x. So we are going to write down the solution for this simply equals to arctan of x. So that finished up the integration for the c term. Next, we go to the integrations that involve the dx term. The integration of d term can be performed by using substitutions of y equals to x squared plus 1. The differential of y will give you x dx, which will be used to substitute the expressions in the numerator, where x dx now becomes dy over 2 and y squared. So that reduced to minus d over 2 times y in the denominator, which is x squared plus 1. So that is the integrations for the d term. Next, we go to see how we integrate the e term. To do this integration, you have to substitute x equals to tangent theta. Then you just write a triangle to represent the formula here. You have a theta here. Tangent theta is the ratio of the opposite to the adjacent. The sine expressions in terms of x, which is by definition the ratio of the opposite divided by the hypotenuse, the x plus x squared with a square root. The definitions of cos theta is the opposite divided by the hypotenuse. You can then write down the differential of x, d dx of tangent theta, dx secant square theta, d theta dx dx. So we have dx equals to secant square theta d theta. We can then translate the integration into the form secant square theta d theta divided by x squared plus 1 squared. X squared plus 1 squared is simply obtained from the substitution rule. So if you have x equals to tangent theta, you can then simplify the x squared plus 1 in the form of tangent squared theta plus 1 secant squared theta. So the square of x squared plus 1 is simply equals to secant raised to the power 4. Therefore, here you have secant power 4 theta. It will give you cos square theta d theta. To integrate cos square theta, you just have to recall the identity of cos 2 theta. 2 cos square theta minus 1. The integrations of cos square theta d theta amounts to half of sine 2 theta divided by 2 plus theta, and you have an constant. So here cos square theta integrations will give you half of sine 2 theta plus an constant. Sine 2 theta is 2 sine theta cos theta. So if you divide this by a factor of half, then this will be cancelled off. So you get sine theta cos theta plus theta of half. We can further simplify sine theta and cos theta into variables x. So sine theta, as we have shown here, is x over square root of x plus half, and cos theta is this. So if you take this and combine it, sine theta cos theta is simply equals to x over 1 plus x squared. X over 1 plus x squared. This is what sine theta cos theta is, plus theta over 2. So if theta is parameterized in terms of the substitution rule, you can from here express theta in terms of x as arctangent of x. So you have a factor of half and arctangent of x plus n constant. Put everything together. Finally, we obtained the equations of integrations for 1 over x squared plus 1 and the whole thing squared. It has been a long discussions. We have shown you how to perform the integrations of each partial fraction terms a, b, c, d, and e. Putting everything together, the slides here is a summary of the result that we obtained from the previous steps. To obtain the constant a, b, c, d, and e in the partial fractions, we just have to sum up the three partial fraction terms into the following form, where the denominator is made up of the common factors appearing in the denominators of the partial fraction. The a terms has to be multiplied by x squared plus 1 squared. The linear factor term bx plus c is to be multiplied with x and x squared plus 1. The linear factor term dx plus e is to be multiplied by a factor of x. We would want to open up the brackets in the function that appears in the numerator. The first bracket to be opened up is the terms that contains a. The second term to be opened up is the term involving b and c, bx power 4, cx power 3, bx squared, and cx. The term involving d and e is simply dx squared plus ex. So we are now in a good position to collect all the coefficients to the powers of x. First, we collect all the coefficients to x power 4. So this is the term a and b. For the coefficients to x power 3, it is contributed only from the c term. For the coefficient of x power 2 term, it comes from 2a, b, and d. The coefficient to x is simply contributed by c and e. The coefficient that is associated with x power 0, which is a constant, comes from the term a only. So now we can identify the numerator function with the numerator values of 1 in the rational function of r. Specifically, the coefficient to x power 4, a plus b, should be equals to 0 because there's no term of x power 4 in the numerator of the function r. We can write ab is identified to be 0. The coefficient c to x power 3 is also 0. The coefficient to x power 2 is also 0. So is the coefficient to x is also 0. The only term that is not 0 in the denominator functions is a. which is simply equals to 1. So up to this point, we have constructed the simultaneous equations for A, B, C, D. There are 5 simultaneous equations here and also 5 coefficients. We solve A equals to 1, C equals to 0. B can be easily solved to be just equals to minus A, and it is minus 1. From this term, E is equals to minus C, which is 0. And from here, D is simply obtained to be minus 1. So the conclusion is the constant A is 1, the constant B is minus 1, the constant C is 0, the constant D is minus 1, and the constant E is 0. So up to this stage, all the constants of A, B, C, D, and E in the 3 partial fractions of R has been obtained. As a conclusion, we have discussed the integrations of an fractional function with a repeated irreducible quadratic factor in the denominator. We first showed how to decompose the fractional function into 3 partial fraction terms. The first partial fraction terms a over x come from this linear factor. The second term comes from the irreducible quadratic factor x squared plus 1 raised to the power 1. And the third terms come from x squared plus 1 squared. Once the fractional function is decomposed into the partial fractions, then the integrations of the fractional function can be integrated term by term based on the expression of the partial fractions. There are a total of 5 integrations to be performed. The A term, B term, C term, D term, and E term integration has been shown explicitly in this video, and we obtained the result of the integrations as shown in this line. We also shown how to obtain the values of the constant term A, B, C, D, and E by equating the coefficients to the powers of x to the coefficients in the numerator of the original fractional function.